Welcome to MET 200 Manufacturing Processes and Material. This is Dr. Hamid Isazadeh, and this lecture we will talk about metal forming. This is lecture 15. In this lecture, we cover chapter 19, which is sheet metal working. It has cutting operations, it has bending operations, drawing. We try to cover some of the most important parts in this lecture. In the sheet metal processes, we have three major categories. One is cutting process, one is bending, and one is drawing. All these processes are performed on the very thin sheet metals between 0.5, 0.4 millimeter up to 6 millimeter, or between 1/64 and a quarter inch size. And the plate, the type of material we use is low carbon steel, which has carbon between 0.06% up to 0.15%. And because it is low cost and it has a good formability and as well as a good strength. The material thicker than quarter inch or 6 millimeter is called a plate, and the process for that material is different. The first sheet metal work-in process is cutting, and here in this schematic, as you see, we have different stages for the cutting operation. In the first one, we have the punch, which is approaching toward the plate, and then in the second step, we have some plastic deformation on the upper surface of the sheet metal, and then we have in the step 3 we have penetration on the sheet metal. The last step, fracture, is initiated at the opposing cutting edges, which separates the sheet. This area is called rollover, and this corresponds to depression made by punch in the workpiece before the cutting process. And the thickness of the sheet metal, as I said before, varies between 0.6, 0.4 millimeter up to 6 millimeter, and operation normally is done at a low temperature. When I say low temperature, means it's in room temperature, like 25 degrees Celsius, or about 75 degree Fahrenheit. On the shear edge of the sheet metal, we have several features. As you see here, we have a rollover, we have burnish and fracture zone, as well as the bear. Starting from top, the rollover, that is corresponded to the depression made by punch before a cutting operation, and this is where the initial plastic deformation occurs at the workpiece. Below the rollover, we have a smooth region called burnish, this area, and that is the result of penetration of the punch into the workpiece, right before the fractures begins. And the third feature is called fracture zone. This area, which is a rough surface, and that is due to the continued downward movement of the punch. Finally, we have the bottom of the edge is called burr, and it is sharp corner at the edge of the sheet metal. Burr actually happens because of the elongation of the metal during final separation of the two pieces. These are the advantages of the sheet metal parts. High strength, for example, we have good dimensional accuracy, the surface finish is very good, we have relatively low cost, and it is designed for mass production of large quantities. Here we have the terminology for the sheet metal working. For example, punch and die tooling, which are used for the cutting operation, bending and drawing. We have a stamping press, and this is the machine tool that performs the sheet metal operations. The last one is called stampings. The products of the sheet metal working is called stamping. These three processes, shearing, blanking, and punching operation, all of them can be performed in the stamping press machine, and they are similar, but there are some differences. For example, the shearing operation, we use that cutter to cut the stock to the size. As you see the front picture, it is a shearing operation. Then on the bottom we have blanking. Blanking and punching, they look similar, but that cut piece, as you see here, is called blank, but in the punching, that cut piece is called a scrap. Clearance in sheet metal cutting is an important factor, and that clearance is the distance between punch cutting edge and the die cutting edge. The typical value is between 4% and 8% of the stock thickness. In this picture, we have two scenarios, A and B. The case A, we have two small clearance, so it's too tight. The fracture lines, as you see, they don't pass each other, which causes double burnishing or a larger force. If it is too large, the clearance on the picture B, the metal is pinched between the cutting edges, and we have a rough surface. Excesses burr can be obtained through this operation. There is a recommended clearance for the cutting operations, and that is called C, and it's a function of the clearance allowance and the stock thickness. And that allowance is determined based on the type of metal. For example, if we are working with aluminum alloy, AC, or the cutting allowance is 0.045, and if it is 61 ST aluminum, that allowance goes up, so you have a larger clearance. For the steel, it's even a larger value, it's 0.075. When we want to design punch and die sizes in the sheet metal cutting operations, we have to look at the diameter of punch and diameter of the blank. So it's important which one we look at. For example, if we are looking for the blank, the diameter of die is important. So as you see here in this equation, blanking punch diameter has to be equal dB minus 2c. dB is the die size, the diameter of the die, and c is the clearance. And if we want to design a punch, if we want to create a hole, then the punch diameter becomes important, and you have to use this equation. Hole diameter equals dh, which is diameter of punch, plus 2c. Another way to say the die size determines the blank size, and the punch size determines the hole size. The next factor is called angular clearance, and that is the degree between this surface, the die surface, and the vertical line. And this angle allows the slot or the blank to drop through the die. And the typical value for this clearance is between 0.25 and 1.5 degree. We can determine the press size for the sheet metal cutting operations based on the cutting force, and the cutting force can be calculated by this equation. We have S, that is the shear strength of the metal. T is the stock thickness, or the plate, or the sheet metal thickness, and we have the length of the cut edge. The length is going to be the perimeter of the blank or the hole. The next operation in the sheet metal working operation is called sheet metal bending. As you see in this schematic, we have a straining of the sheet metal around the straight axis to take a permanent bend. If we look at inside the workpiece, we have a neutral axis, which is this one. The metal inside the neutral plane, somewhere here, that metal is compressed, and metal outside here, as you see, it's a stretch. So we have tensile stress this area and compressive stress on this region. There are two types of sheet metal bending. One is called V bending. The second one is called edge bending. The V bending is performed with a V shape die, like this picture. It shows before bending, and this one shows after bending. And the application for the V bending is for a low production, and it is performed on the press brake. This operation is simple, and it is inexpensive. On the other hand, we have edge bending, which is performed with a whipping die, and here we have two steps for the edge bending. before the bending, and this is after bending process. And this process is used for high production, and it requires a pressure pad. As you see in this part, we have pressure pad, and dyes normally are more complicated, and it is costly. In the sheet metal bending operation, we have one phenomena that is called a spring back, and that is the increase in angle of the bent part relative to the angle of forming tool. As you see here, when the punch is removed, this part has a larger angle compared to the punch. The main reason is that we have some elastic energy that remains in the bent part. So the part does not have full plastic deformation. And because of that elastic energy, um, that recovers some of the original shape of the metal. There are two methods to address this issue. It's called overbending. The second one is called bottoming. In the overbending, the punch angle and radius are fabricated slightly smaller than the specified angle on the final part, so that the sheet metal springs back to the desired value. The bottoming, however, involves squeezing the part at the end of the stroke, which creates plastic deformation at that bend region, which is this area. The next operation is called drawing process. In this sheet metal forming process, we can make a cup shape, box shape, and other complex curved parts. The beverage cans is one example of the drawing operation. In this operation, the blank is positioned over a die cavity. As you see in this picture, we have a blank, this part, and then we have a punch, this part, that pushes the metal into the opening. And here is the final part. But remember, if the punch and die were to have sharp corners at these edges in this area, what happens? A whole punching operation would take place. But here, because we have smooth corners, we won't have a hole in that blank. Sometimes we call the drawing process deep drawing, and the steps for the deep drawings is shown here, starting from the number 1. We have the punch just before the contact with the workpiece. There is a small gap between them, and then we have a bending as the punch first begins to push into the workpiece. The metal is subjected to bending operation at that point, at that moment. Then that blank or sheet is simply bent over the corners of the punch and the corners of the die, this area. The next step is this. We have a straightening. See this punch moves downward. um, Step 4, we have compression as well as some friction between the die surfaces as well as the punch surface. The final process is this one, where we have the final cut shape, which shows the effect of thinning in the cup walls. Like other metal forming processes, clearance is important. The clearance can be calculated with a certain equation, which is this one, and this equation may vary depending on the material, but it's a general equation, and it says clearance is 1.1 times this stock thickness. Okay, as you see, the clearance is 10% greater than the stock thickness, and this value is greater than clearance we see in the cutting operations. Why is that? The main purpose is that if you reduce that clearance to a smaller value, and then we have cutting operations, so we won't have drawing. The material will fail during the drawing operations, so we don't want that happen during the drawing process. Generally, the drawing operation is more complex operation comparing with the cutting and bending operations. And because of that, we have various defects in the drawing operation. Some of them are listed in this schematic, as you see. For example, we have a wrinkling, and that is it consists of a series of ridges that formed radially in the flange. This is due to compressive buckling. The next defect is this one, where we have wrinkling in the wall. If the wrinkled flange is drawing into the cup, these ridges appear in the vertical wall, and that is a defect. This is not we wanted from this process. The next defect is tearing. Tearing is an open crack in the vertical cup, and it is usually happens near the base of drawing cup here. And this is due to the high tensile stress that happens during straightening or thinning. And this type of failure can also happen when the metal is pulled over sharp die corners. The next error or defect is called earring, and this is the formation of irregular shape on the top edges of the cup here. This is not desirable, and this is normally caused by the anisotropic property in the sheet metal. If the material is perfectly isotropic, ears like this won't happen. The next defect is called surface scratches. The surface scratches may happen on the drawn part if the punch or die are not smooth, or we don't have enough lubrication between the die and punch. We talked about cylindrical cups so far, but it is possible that we use deep drawing to make other geometry, but each geometry has its own no problem. Like a square, rectangle, boxes, it's going to be more difficult. We can make a stepped cup, we can make cones, also cups with a spherical rather than flat base on the bottom. Like if you make a cup, the bottom part has a spherical or this shape. It's not flat anymore, so it becomes more difficult. Or we can have irregular curve that we use a lot in the body panel in the automotive industry, and those are um, some of the deep drawing that is unique, and each one has its own issues and problems. In the sheet metal processes, we use conventional punch and die tooling equipment. We may have some custom design for the particular part, and but most of the times the equipment will be the same. Like this machine, as you see, it is used for metal forming process. It has punch and die components. It's this area, this component is die, and we have a die set. The lower portion is the die holder. The upper portion is called punch holder, and the die set includes a guide pin and bushing to make sure we have a proper alignment between punch and die during stamping operations. This area, this element is guide pins, and on the right side also. And here, the actuation of that ram accomplishes the press working operation. This machine is a stamping press, and it has a component shown. For example, this part is a frame. We have a flywheel, which is connected to electric motor or a hydraulic power to drive that ram. And we have a punch holder attached to the ram, as well as the die holder attached to the bolster plate of the press bed, this part. There are two types of stamping press frame. One is called gap frame, which has a letter configuration, this one, and sometimes they call it the C frame. The benefit of the gap frame is that it provides a good access to the die, and because they are usually open in the back, so it allows the convenient rejection of the stamp or the scrap metal. We have other type. It's called a straight side frame, which is designed for a higher load for higher tonnage. In addition to bending and drawing operation that we discussed already, there are several um, related sheet metal forming processes that we want to mention. First one is called ironing. Ironing operation is designed to achieve thinning and elongation of a wall, um, and the process, as you see, is shown in this schematic. The dies, this is the die, and this is the punch, and this ironing, as you see, the die is not completely straight. It has an edge somewhere here, and it makes the cylindrical cup more uniform in the wall thickness. And the part is longer, and it's going to be more efficient in terms of the material usage. Example can be beverage cans or shells that we need for high production. The next operation is called embossing. This operation creates indentation in the sheet, such as raised, like this example, or indented lettering on the sample. The next process is called a Gering process, where we have a thick rubber pad right here inside the steel container. And this thick rubber pad is used to form sheet metal over a positive form block, which is this one. And as the ram descends, the rubber gradually surrounds the sheet and it applies pressure to deform it, like this picture as you see, to deform it to the shape of the form block. There are some advantages for this process. It has a low tooling cost. The form block can be made of wood, plastic, and other material that are easy to shape. The same rubber pad, we can use it for different form block. And this process is good for the small quantity, not for high quantity. We have other forming processes that are not performed on the presses, like stretch forming. We have roll bending and forming. We have spinning, and we have high energy rate forming processes. The first process was stretch forming. In this process, we have the sheet metal stretch. As you see, this is the sheet metal. We have two jaws, and it applies tensile stress. So we have some pre-stress in this sheet metal. Then we have a die like this one that applies a pressure on the sheet metal. Because there are some pre-stress in that part, it will be easier for the sheet metal to deform. Similar processes can be done on the tube, and it's called bending of tube stock. And we have a gripper at on the two end of the tube, and then we have a form block. As you see, this form block or die change the pipe like this shape. Somehow we have a bending at the mid center of this pipe. We can also draw the tube and bend it like this picture, as you see. So we have a clamp right there. It holds the end of pipe, and then the form block rotate clockwise. Then we have a bending plus a drawing on the pipe. So we can have a 90-degree on this pipe. The last category is called high energy rate forming process, HERF. This is a process to form metal using a large amount of energy. The time in this process is very short, and it can be done with explosive material. It can be done on electro-hydraulic equipment and electromagnetic equipment. In the explosive forming process, we use explosive charge to form sheet or the metal into the die cavity. As you see in this picture here, we have explosive charge at this point, and we have a liquid right here. It can be water or other liquid, and then this explosive charge is detonated, and it creates a shock wave like this picture, and that shock wave forms the part. Finally, if we have the desired shape, it takes the die cavity shape, and it has a lot of application in the aerospace industry, mostly for large parts, and it is expensive because of the equipment and the safety that has to be taken during the process. The next high energy rate forming process is called electromagnetic forming process. Here we have a sheet metal that is going to be deformed by mechanical force of electromagnetic field that is induced in the in the workpiece. And the coil, as you see in this schematic, that coil, which is energized by a capacitor, produces a magnetic field. That magnetic field generates eddy current in the workpiece here. And that eddy current in the workpiece produces its own magnetic field here in this pipe, for example. And that induced field will be opposite the primary field, and it generates a mechanical force, and that mechanical force will deform the part like the surrounding cavity. So we have this, for example, the shape. So we have two type of forces. One force is coming from this coil, and one force is going to be generated in the pipe. So these two forces interact with each other, and then the pipe will take the shape of the die, which is this shape.